This is the first of two lectures covering Chapter 1.1 to 1.3 in the Blitzer book, Graphing Functions. We're going to start off by defining several words that we're going to be using in this chapter. In particular, function versus relation, domain and range, what minimum, maximum, increasing and decreasing mean, and how to calculate x-intercepts and y-intercepts, as well as even and odd functions. Okay, we're also going to get a little bit of practice using our graphing calculator. The second lecture will focus on the piecewise graphs, absolute value, and difference quotient. First off, anytime we collect data, okay, or relate two sets of data, we are establishing a relationship between those two variables, okay, the input variable and the output variable. For instance, let's collect data for a person's shoe size versus their height. So we're trying to relate their shoe size to their height. This is some sample data that was collected, okay? We have people's height, 165 centimeters, and their shoe size was an 8, all the way down on the bottom, 160 centimeters with a shoe size also of 8. Okay, so looking at the data, there is a relationship between a person's height and their shoe size. As you would imagine, as the person's height generally gets taller, their shoe size would get bigger. Okay, however, the output variable shoe size can be different for the same input variable. Okay, if you look at numbers 3 and 5, okay, people 3 and 5, they're both 144 centimeters tall, but their shoe sizes are different. Okay, person number 3 has a shoe size of 5, person number 5 has a shoe size of 6. Therefore, okay, this is what we call a relation. Okay, relations can have any kind of relationship between the input variable and the output variable. A function, on the other hand, okay, only has one possible output variable for the same input variable. So 3 and 5, the input variable is height of 144. The output variable is 5 or 6, depending on the person. So this is what we call a relationship. Okay, another way to describe this is using a Venn diagram. Okay, all functions are considered to be relations, okay, but not all relations are functions. Okay, anytime the input variable results in multiple output variables, that would be a relation. Okay, and yet a third way we can look at this. Okay, if we have a graph of the function, okay, there's something that's called a vertical line test. Okay, and on a graph, if I can draw a vertical line on the graph which touches the function at 2 points, then it is actually not a function but a relationship. So for instance, the first graph is a graph of y equals plus or minus square root of x. Okay, and if I draw a line here, okay, I actually touch the graph in 2 spots. Same with the circle on the side here. Okay, if I draw a line, a vertical line, it touches the circle at 2 different points. Therefore, those two are considered relationships and not functions. Okay, the bottom 2 are functions because I can't draw a line that touches the graph at 2 points. Okay, even so, if I draw it here or if I draw it here, it only touches at 1 point. On this one, even if I draw it right here through the 2 dots, okay, the middle line has an open dot, so it doesn't actually touch that number. Yes, the bottom line does, but because they don't overlap, I'm only touching this function in 1 spot. Okay, so moving on, domain versus range. Okay, the domain is the set of input variables and the range is the set of output variables. Okay, so on a graph or a function, we usually think of the domain as the x variable. What are the possible range of x variables? What is the possible range of y variables? Okay, so in the function on the bottom, just looking at the graph, it looks like x is greater than or equal to 1. And the y value looks like it can go from plus infinity to minus infinity. Okay, and in the first case, okay, y is equal to 2x squared, the domain is basically x can be any number, plus infinity to minus infinity. But the range, okay, because even if it's a negative x, y will always be positive because when I square a negative number, it'll become positive. So the range is just y greater than or equal to 0. In interval format, okay, this would be represented as bracket 0 greater than or equal to all the way up to plus infinity. Okay, and infinity is always in open parentheses. Okay. You can have a domain and a range even if the graph is not a function. Okay, so yes, the graph in the bottom, that's not a function, but you still have a domain and a range. Okay, domain and range on a graph. Okay, the domain and range are usually infinitely large sets and they can't be shown on a graph. So you do need to be careful that your graph is sufficiently zoomed out to see enough of the graph. Okay, so let's take a look at our calculators, in particular the TI-80 through 84. Okay, and if I want to graph a function, okay, I can start by entering the function here on y equals. Okay, I already have a function, so I'm going to clear that one out. Okay, because the function I want to graph is the one on the page, which is 1/9 x squared. Whoops. 1/9 x squared, arrow out to get it out of the exponent, plus, it was actually 1/9 x cubed minus 2x, 1/9 x, 1/9 x cubed minus 2x squared plus x minus 3 plus x minus 3. Okay, so there's where I enter the function. Okay, and when I want to graph it, I would just hit the graph function. Okay, and right now my zoom is off, so I can't actually see the function. So what I would want to do is hit zoom and then 6 for standard. It'll zoom out to a standard view of the function. And so this is what I see when I do that. Okay, but this is just a small view of the function. Okay, so, and I'm missing some important elements. So you do need to be very careful when graphing your functions to make sure that you are sufficiently zoomed out. Okay, to zoom out, I can hit zoom 3, okay, and then the cursor gives me a flashing cursor, so I'll move it off. You can kind of see it there. Okay, and what I want to say is zoom out using this as my new center point. So I hit enter and it zooms out and I see, oh, there's something more going on here. If I zoom out again by hitting enter, I see that there is definitely something that I missed in the first part. Okay, so I'm going to change my zoom window, okay, to the values shown here, which is -10, 50 and -100, 100. Okay, so -10, whoops, window, -10, down. I keep hitting the minus sign. Okay, sorry. Window, -10, go down, +50, go down, skip the scale, set it here, and we're going to go on this one, we're going to go from -100 to 100. So -100, arrow down, 100, and now graph it. Okay, and this gives me a much better view of the graph. Okay, so always be careful and know what you're graphing and whether there might be something off screen that you need to zoom out for. Okay, so let's go back to the presentation. Okay, minimums and maximums. Okay, the graph on the right is the graph of the same function from the previous slide. I know it says left, but I mean right. Okay, so looking at the graph, there appears to be a maximum value somewhere around x equals 0 and a minimum value. What it means to be a maximum value is if I move even one little dot to the left and one little dot to the right, those f of x's will be less than that maximum. For a minimum, if I move one little bit to the left, one little bit to the right, those will be greater than the minimum value. Okay, and so these 2 points at x equals 0, or roughly x equals 0, and x equals 12, are only local maximums and minimums. Okay, meaning that they're only a maximum and minimum in that little range. Okay, because the absolute maximums and minimums are actually going to be plus infinity and minus infinity on this graph. Okay, because I can't actually show them because it's infinity, but if you can imagine the lines keeping on going, they will reach infinity. Okay, increasing and decreasing intervals. Okay, a function is described as increasing in a specific section or in a specific interval. Okay, if the output value f of x increases as the input value increases. So on a graph you would ask yourself, is the function going up? So in this first section here, okay, my graph is going up, and in this section my graph is going up. So I would describe this as saying, well, from minus infinity to roughly 0, it's not actually 0, but we'll figure that out at some other time. Okay, I am going up. Okay, using parentheses, they're always going to be open intervals. Okay, the other region that it's also doing that, it looks like to be from positive 3 to plus infinity on the x-axis. These are all x values. Okay, similarly, I can describe it as decreasing. Okay, so this could be decreasing here. Let's see, let's choose a different color. How about red? No, I just red. Let's choose yellow. Okay, in this region here, okay, it's decreasing because as I move to the right, my f of x gets smaller and smaller. Okay, so I would say in this area, from roughly 0 to plus 3, it's considered decreasing. Okay, so remember to always use open intervals for increasing and decreasing intervals. The last thing I want to cover is even or odd. Okay, functions that are symmetric across the y-axis are described as even. Okay, so if I take the piece of paper and I fold it along the y-axis, the two sides of the axis will just overlap each other. Okay, mathematically we can test to see if a function is even by just testing to see is f of x equal to f of minus x. Okay, if my function is a polynomial and all the exponents are even, then the function would be considered even. Okay, functions that are going to be symmetric across the origin are a little bit harder to tell. Okay, but in terms of a graph, if I fold the graph first along the x-axis and then fold it along the y-axis and they overlap, that's considered symmetric across the origin. Okay, the algebraic test for this is if f of x equals minus f of minus x. Okay, for a polynomial, again, if all the exponents are odd, my function will be odd. Okay? We're going to save piecewise functions for the next lecture. Thank you.